Thank you all. I see some names online. Thank you for joining us in person or via Zoom. My pleasure to be here today. My name is Maria Silveira. I'm a soil scientist here at the Research Center. And today I'm going to provide you with an update about our LTAR project. A lot of you probably heard about me talking about LTAR, but LTAR is this acronym that refers to the Long-Term Agroecosystem Research Network. So this map is the map of the United States, and each dot in the map represents an LTAR site. Currently, we have 18 sites. So you see the different, I don't know if the folks in the room can see the different colors, but there's some sites that have a brownish color, some sites have that greenish color. So the browns are great. The brown color represent the sites that have grazing lands, and the green are the cropland sites. And we also have a couple integrated crop livestock systems. So we work together in this network to address questions related to agriculture production, but also the network is heavily focused on these three pillars of sustainability. So the rural prosperity, the environmental impact of agriculture, but we also want to increase ag production. So when you compare LTAR to some of the networks that you may have heard before, LTAR or NEON, one of the differences that LTAR is heavily focused on ag production. So we're working on agricultural working lands, and we're trying to address issues related to ag production and, like I said, environmental impact and the social and economic impact as well. So if you're interested in learning more about the network, I'm not gonna, my presentation is only 25 minutes. I encourage you to go to this website. It explains the network, but there's also, if you have access to the scientific journals, there's a new issue on GAQ, the Journal of Environmental Quality is one of the journals that my group publishes a lot. And this December issue of GAQ is a special issue that describes the LTAR network. So each of those 18 sites have a paper there and explains what the treatments entail, what their research goals are. And of course, we also have one paper there. This refers to our site. Also, recently, the LTAR and the Research Center was featured in this CSA News. Those who are not part of so the CSA News is a magazine for the Agronomy, Crop Science, and Soil Society of America. So I looked at just to have an idea how many active members this prize society has, and it's about 8,000 people. So the last issue, or not the last, the October issue, the last issue was November, it's featuring us on the front cover, which I wasn't expecting, but also if you flip the second page, it's featuring the Research Center, and it describes our LTAR efforts. So it was a very good, nice recognition of our work. We're a joint site. So as you probably saw in that first map, we are partners with Archibald Biological Station. I know that some of you visit Archibald. So our LTAR efforts we're conducting in collaboration with Archibald. So if you look at the map, we are the yellow dot in Hardy County, and Archibald is only less than 50 minutes away from us. So we represent this land use gradient. So combine Archibald and University of Florida, we have this range of different management systems that goes from minimally managed native rangelands to more intensively managed cultivated pastures. So together, we look at how managing these ecosystems can affect production, cow-calf production, forage production, but as well as the multiple ecosystem services associated with this landscape. So I forgot to mention that I think most of you know the colors in this map represents cattle inventory. So both sites are strategically located in the heart of the cattle production in Florida. So now I'm going to switch over. I mentioned that Archibald and University of Florida were partners, and we have different treatments associated with these different pasture types, if you call. And for today's presentation, I'm going to be covering what we do at the University of Florida site. And so we have what we call COMO experiments. Those are areas that we collect a lot of data and share with the network. Those are the experiments that we're calling COMO experiments. We have COMO experiment. And we have two different efforts going on here at the Research Center. One is in the native rangelands, where we're using prescribed fire to manipulate the vegetation. So I'll explain more details, but you see here control plots that haven't been burned for a number of years, plots that are burned either at every 4 years or every 2 years. And we also have a fourth treatment that is a combination of prescribed burning plus mechanical chopping of shrubs. In the Bahia grass pasture, we also have another project. And we're dealing with different stocking rates. So we have pastures that have certain stocking rate and pastures that are graze under heavier stocking rate. So just briefly, just want to mention the scale. So these are relatively large for context of research that we normally do. So these are we have, for instance, in the native rangelands, we have 16 blocks. They're about 40 to 70 acres each. You see the different colors representing this map. So the fire treatments that I mentioned before are replicated 4 times in these different blocks. You see those dot lines here. Those are permanent transects that we use as reference to collect a lot of the data. So the vegetation data, soils data, greenhouse gas data, we use that as a reference. You also see this circle here in this red block. This is the Woods 2, Unit 2. Some of you may know where I'm talking about. And the star in the middle represents an eddy covariance tower. And so right now we have 2 of this eddy covariance equipment, which basically is a micrometeorological technique to measure carbon exchange between soil, plants, and the atmosphere. So in terms of treatment, I mentioned the 4 different treatments. So burned is our control. The blocks that are burned every 4 years represent what is most common in this region. If a producer has a native rangeland, usually if they can use prescribed fire, they'll burn the native rangelands every 4 years. So we also decide to increase the frequency of fire and combine fire with the mechanical control of palmetto. And those native rangeland areas are grazed in the winter for about 90 to 100. We extended a little bit. The slide here says 90 days, but we extended a little bit to 120 days. And I'm going to mention this. A lot of the REC faculty here are involved in this project. Dr. Vendramini, Muriel are involved. Now we're using virtual fence in the woods to see if there's any difference between rotationally grazing these areas versus continuous stock. So there's a lot of different questions from different areas of expertise that we're trying to address. One thing, I'm not a fire expert by no means, so I'm afraid of fire, but fire is a pretty interesting disturbance. Disturbance, not with a negative connotation, but treatment that we evaluate. I think there's yeah. So this is how burning in the woods look like when it's happening. You see the distance that I'm filming because I'm just easy to get closer. It's a pretty interesting process if you've never seen it. In terms of the timeline for the project in the native rangelands, we started collecting data. Our involvement with LTAR started probably in the 2016. We started collecting data in 2017, so pre-treatments. And the treatments were first imposed in 2019. So you see this mark here. That's when the treatments that were supposed to be burned were burned the first time. And then from then on, we'll continue with that, what I already explained. So what's going to happen next year? The treatments that are burned every 2 years will be hopefully burned next year, 2025. So now I'm going to switch over to the cultivated, the Bahia grass pastures. We have 16 paddocks. We also have, you see here representing this map. Half of those are grazed at a stocking rate of 0.66 animal units per hectare. And the other half, we increased the stocking rate by about 20% only. So the rationale was when and these pastures are fertilized every year, they're rotationally stocked. So that lower stocking rate is probably what would be the most common in the region. And so the idea was, how can we increase production in these systems with trying to maintain the same inputs? That's why we came up with this idea. Well, can we produce more calves, have a greater production? And if we do, what will be the potentially negative impact in terms of gas production, soil health, and etc. So that's what we're doing. This is relatively newer. where is still ongoing, so I'm not going to be sharing a whole lot of data. Like I said, other faculty are also involved. Joe and Philippe are doing other measurements, forage evaluation, animal performance. So in the end, once we complete this project, it will be very interesting to see what the benefits and the potential trade-offs will be when we increase stocking rate. And I mentioned there's also a eco-variance system here. One of the main, especially for folks, that individuals that are not necessarily involved with agriculture, there's this very negative connotation associated with cattle production and methane emissions. So the eco-variance is one way for us to measure how much is that methane contribution from these pastures. So in the end, we're gonna hopefully be able to quantify that. More recently, we decided to include, this is not part of the Como experiment, but it's also another research question that's related to the LTAR. The idea of incorporating trees, in this case is pine trees, grow in conjunction with the Bahia grass pastures. So we are in the process of installing another eco-variance tower in the silvopasture system. We've done some research with silvopasture systems and we quantify carbon accumulation, but now those systems were pretty much mature trees. So now we want to understand from the beginning, once you establish a silvopasture system, to how long it takes for the trees to actually start accumulating carbon and changing the carbon balance when you compare to grass pastures alone. So this is a relatively new project and we're still instrumenting, but I think there are not many and silvopasture systems that are used for research. So I think it'll be very interesting to see what happens over the years with this project. So not going to be sharing any data relative to this project either. In terms of measurements, I think I mentioned a couple of the things. So the different experiments, there are certain things that we measure that are common across all the different experiments. For the range, that because we're manipulating fire, during the fire event, we measure a number of different parameters because that's help us understand the responses that we measure later. Vegetation, we measure composition, biomass, soils. There's a number of soil parameters that we're looking at from well, it ranges from things that are more agronomically related to some other things that are more environmentally related. We also measure greenhouse gas using different techniques, the chamber or the eco-variance. And with the help of my colleagues, we can also measure animal responses. So I'm going to share just a little bit of the data, and that's different. I know every year I present this. So this is this presentation. This one has some newer data. And I've shared this picture before, but I think I'm still, I don't know what the word is, surprised with the rangeland vegetation. So this is, the picture in the middle shows how the palmetto and the woods vegetation look like the day of the fire. So of course the fire is not a homogeneous process. There's some patches that are not necessarily completely burned. Some are completely burned, like this particular spot here. So this is day 0. 5 days later, you can see the plants greening. And this is, by the way, I think I mentioned, but this is palmetto plants. You see the greening happening only 5 days after the prescribed fire. And if you come back like a month later, in this case, this picture was taken 18 days after the fire, you can see significant growth. So these landscapes, they evolved under fire. So the plants recover quite fast after that disturbance. In fact, I'm gonna show in another slide that with the eco-variance, we can kind of quantify how long it takes for the vegetation to fully recover after fire. And it's amazing. In our case, maybe some of you, so if you know the answer, don't say, but if you don't know the answer, would you like to guess how long it takes for the vegetation to go from that center picture to fully recovered? So that fully recovered means they are producing the photosynthesis rate are the same as before fire. So what do you think is that? Couple months, couple years, decades, days? Give me a guess. 45, what, days? 45 days, that's right. So from that, okay, 45 days, Clay is saying. Anybody disagree with Clay? Okay, the answer is 60 days. This is extremely fast because of the conditions are warm and our environmental conditions are conducive to plant photosynthesis, but also these plants, like I said, they tolerate fire. So it's amazing. You can almost, if you pay close attention, you can almost see the palmetto growing. And the native grass is the same. It's amazing how quickly they recover after fire. So whole idea of using fire in these ecosystems is to suppress some of the shrubs. In this case, the predominant species is this we call palmetto. So it's not to eliminate, but suppress the palmetto so we can promote the growth of native grasses. So in this case, chalky blue stem, Indian grass, some of the grasses that we call desirable from a livestock perspective. So when we look at the impact of this, and this is new data compiled from 2017, so pre-treatment up to last year. When you look at the impact of these different treatments, the main impact, and I'm not gonna go over every single line in this table, but if you look at, for instance, palmetto here, as you increase the fire free, and this is biomass, above ground biomass in grams per square meter. So if you don't burn palmetto, you have this amount of biomass. If you burn every 4 years, there's no statistical differences. So you burn every 4 years or you don't burn, you're gonna have the same palmetto biomass. But once you increase the fire frequency, you reduce that palmetto biomass. Now, if you combine fire with chopping, then you reduce even further. One of the issues that we saw with chopping and is that, yes, it reduces palmetto. And what we want is to increase these desirable grasses, desirable again from the livestock perspective. So yes, any of the treatments that we evaluated involving fire increase the proportion of this desirable grass species. But the problem with going back to the mechanical chopping is that we also increase, by chopping and by disturbing the soil, we also increase a lot of the undesirable species, especially undesirable grasses. So we disturb the seed bank and yes, you reduce palmetto, but at the same time, you promote the growth of certain species that are not necessarily desirable for cattle production. So there's also a year effect. It's interesting. So there was not a treatment by year. So only the single effects were significant. There was not an interaction. So it's interesting to see. So this is a average across all treatments. It's interesting to see the ones that are lowers that are the treatments that we burned everything, except of course the unburned. But there's also a lot of impact of environmental conditions. So the years that we have more rain, the biomass is slightly greater. So there's quite a bit of variability associated with both the treatments, but also the environmental conditions. So one thing that individuals are always concerned, once you burn, and you saw that picture, almost the entire above ground biomass is combusted, it's gone. What happens to the nutrients that are associated with that above ground biomass? So in this case, we're looking at carbon, nitrogen, and phosphorus associated with above ground biomass, and we have different, I'll tell you the take home message. So we measure carbon, nitrogen, and phosphorus stocks in this above ground biomass. And we have different components of the biomass. So the green biomass, senescent material, litter that was deposited in the soil. So we have an idea how much is carbon, nitrogen stocks before fire. We came back after fire and we measure how much remained. By difference, we could know how much was lost through combustion. And I forgot to mention, we also divided we did this assessment in areas that were dominated by saw palmetto and areas that had more native grasses. So the bottom line is, yes, a significant proportion of the carbon, nitrogen, and phosphorus lost when you burn. However, when you look at the same stocks below ground, so the orange bar here represents roots and soil. So the above ground biomass represents such a small fraction of the total stocks in the ecosystem that really fire didn't have an effect. So for instance, this is the picture on your left-hand side is carbon. When you look at carbon stocks, this is megagrams of carbon per hectare as affected by the different treatments. There was no treatment effect. So even with burning, even with prescribed burn, we didn't impact carbon and nitrogen stocks. And the reason for that is, if you look at, don't worry about this picture in the middle, but if you look at this picture on your right-hand side, so this is one of the parameters that we measure during fire. These are thermal couplers. So we install this at the soil surface and 2.5 centimeters below the soil surface. So about an inch below the soil surface. So when we burn, when we burn and the fire goes through the landscape, that sensor measures the temperature. So there are two lines in this graphic here. The top one you see that peak. You see the temperature associated with that peak is about 600 degrees Celsius. So it's pretty high temperature. That means that the fire was probably going on top of the sensor. But you see the duration, it only lasts between 2 and 3 minutes. And then the temperature quickly drops back to the baseline condition. And if you look at the other line in this graphic, it's a straight line. That's the sensor that was installed at 2.5 centimeters. So that means that, and then you see there's a flat line, that meaning that there is no increase in temperature. So the fire only affect above ground portion of the ecosystem. There's not much impact in terms of temperature increase below that surface. And so the picture that in the middle that I told you not to worry about, those are different bacteria and fungi groups. And we want to know, well, we're looking at from the microbial scale all the way to the ecosystem level. What are the impacts of fire? And even in this very small scale that we expect to see differences, we didn't. So, and the reason for the lack of difference, so the microbes don't change in response to fire. And the reason for that is that the temperature really doesn't increase below the surface. And this is part of PhD student GPT Rai that finished her PhD a few years ago. Also, I think I'm running out of time. I shared this with you. I'm not gonna, this is a paper that Dr. Brashew published a few years ago, and it summarizes carbon fluxes in the native rangelands before and after fire. I think the important, I'll go straight to the important result. So this is the years. This paper only ran from 2016 to 2019. Now we're compiling the data up to this year. So this GPP is a measure of how much the plants are accumulating carbon through photosynthesis. This R equals ecosystem respiration. So plants capture carbon from the atmosphere through photosynthesis. Plants and microbes, soil microbes, release carbon back to the atmosphere as respiration. So what is really important to understand the carbon balance is the difference between how much is being captured, how much is being released back. And that's the NEP. The NEP, if it's negative, that means that the carbon uptake is greater than the carbon release. So that means that the ecosystem is acting as a carbon sink. So you see those numbers. This is, I believe this is grams of, good question. What is the unit here? Yeah, it's grams of carbon per square meter. So you see that NEP is negative for all years that we measure, including the year that we burned the system. In 2019, we burned these woods, and even in the year that we burned, the ecosystem was still a carbon sink. So we also, I think this is one of my last slides. We also compare this carbon balance between the native rangeland with the Bahia grass pasture. So if you look at the black bars, this is again NEP. Net ecosystem productivity. So remember, negative numbers means that the ecosystem is acting as a carbon sink. So you look at the native rangeland, and this is the x-axis months. So each bar represents a month from 2021 to 2024. If you look at the native rangelands, doing throughout those years, most of the months, the native rangeland is a carbon sink. The years that the switch over to being a carbon source, it was usually during the fire, right immediately after a fire event. For instance, fire here, for 2 months, the native rangeland was acting as a carbon sink. But overall, if you calculate on an annual basis, every year it's being a carbon sink. But when you look at the Bahia grass pasture, you look at the size of those bars is much greater. So the Bahia grass is able to, a photosynthetic capacity of Bahia grass is much greater than the native plants that we have in the woods. However, the Bahia grass also emits a lot of carbon in the form of methane. Not necessarily the animals also, but also the soils emit a lot of methane back to the atmosphere. Again, when you look at this balance, how much is being captured, how much is being released back to the atmosphere, and those are the numbers that I have here in this table, comparing the rangeland and the Bahia grass. The larger or the more negative, that means it's a stronger carbon sink. So if despite releasing more methane to the atmosphere because Bahia grass is capturing more, that net balance was more negative for the Bahia grass pasture. So what I want to say with that, I think the take-home message is, yeah, if you want to look at only one aspect, if you want to look at methane is a big, it's a hot topic. If you want to just evaluate methane production under different systems, you're going to say, well, Bahia grass is worse because it's releasing more methane to the atmosphere. However, I think the proper way to address this is looking at as a whole and look at what is the balance. Because again, these warm season grasses are so effective at converting carbon into biomass that the balance becomes much more favorable for the Bahia grass. And this data is not being published yet. So we're hoping that next year it will be available. Finally, I just want to say this is what I'm presenting here reflects a group effort. I'm just a messenger here. There's a number of individuals that are involved in this LTAR, including our partners, Archibald, but a number of faculty here at the Research Center are actively engaged in the LTAR project. Many of you have seen Dr. Roswell Bracho. He's also heavily engaged with our group. And a lot of students that are not putting their names here and postdocs that contributed to this effort. So I just want to acknowledge that my current group and this very nice picture of us here, they are helping with the continuity of this project. I think that's my last. Thank you so much, and I'll be happy to take any questions. We have Congo grass a little bit, but I think the vast majority are native. And yeah, exactly. So that designation of desirable and undesirable is kind of, it's for the livestock perspective. So what is undesirable for livestock could be desirable for wildlife. Could be, yes. Just from the purely nutritive value of that species. Any? I don't think there's any association, no. But you know what? Going back to Hans' question about, so the undesirable in the the treatments that were chopped might be some, we are not doing the evaluation. It's not a species level, so I cannot tell. It's a functional group, but it might be interesting to spend some time in the chopped area to see what it's a lot of weed. Correct, yes. And because the unburned they've been suppressed from fire for so many years. I mean, the vegetation looks completely different. It's a pain to do vegetation assessment because it's becoming pretty encroached with palmetto and other shrub species. So my feeling is that there's probably significant changes in the habitat for wildlife. when I asked that question about how long it takes for the vegetation recovers, when you look at the literature, most ecosystem, even in tropical conditions, it takes years for that, for the vegetation to fully recover. So it's pretty amazing. I think one of the things that I'm more excited about Florida is how quick and how resilient those ecosystems are. It changes really quick, but it also resists. So there was years that I was showing that data that's Hurricane Ian. So a lot of severe weather events, it really doesn't change carbon balance. For instance, I expect all the pleasures were underwater for so many months. So this year we're going to have a significant change in the carbon balance, and not that great, not that different. So the resilience is also something pretty unique to Florida. Any other questions? Oh, a couple of announcements if there's no questions. Okay, well, thank you so much.
So just a couple of usual announcements. We'd like to welcome everybody to come back in December on Tuesday, December 10th for Dr. Golmar Gomohandadi's webinar entitled Groundwater Modeling, Quantity and Quality. And that will be the usual time, 11 o'clock, and I will share that registration info with you when I send you the recording of today's Ona Highlight. We would also like to let you know that South Florida Bee Forage program is doing their Cattle Management for Women event in December this year on the 12th, and that event is going to be in Dade City. Space is limited. If you would like to attend, register soon. Also, keep your calendar open for April 17th. That is our next field day, and it'll be a full day event from 8 to about 3 o'clock in the afternoon with morning presentations and opportunities to see the research that our students are doing, and then some morning talks, a really good steak lunch, and then afternoon field tour presentations. So if you've never been to the center, this is a great time to visit. So I highly recommend watch for that, and we will start opening registration in February. If you're not already doing so, we invite you to follow us on social media. We're on Facebook, Twitter, YouTube, and Instagram. And if you don't get our Friday e-news, just a really nice, easy, newsy email that includes information about the week's happenings, upcoming events, and things that might interest you, just send us an email to ona@ifas.ufl.edu, and we will put you on that email list. Now, our wonderful online Zoom participants, thank you for being with us today. Whenever this event closes, a survey is going to pop up really quick. It won't take you more than probably 3 minutes to complete it. If you don't mind, please do so. We really appreciate your feedback. And we hope to see you in December. Thank you.